Greetings. We're ready for our first workshop of the fall meeting. That means it's an opportunity for journalists to learn about something upcoming that's going to be newsmaking when it actually happens. And this is about something that begins next month. We're calling this Refilling California's Reservoirs, the Storm Aerosols Connection. And Marty Ralph, who's the director of the Center for Western Weather and Water Extremes at Scripps Institution of Oceanography at UC San Diego, he's going to introduce the rest of the panel.
The other presentation up here.
Just mouse over that. There you go. There you are.
There we go. Welcome. Thanks for joining us today, and thanks for Scripps and DOE and NOAA and others helping organize this. The gist of this is about the work we're doing this winter, coming up starting in January, with an experiment that's really focused on the science that underlies how the natural processes can refill reservoirs or even cause flooding, in the state of California. And the major two thrusts are this phenomena called atmospheric rivers, which you saw looping on the screen a moment ago, and then also the role of aerosols in modulating clouds and precipitation. So our panel today is myself, and I'll be talking a bit about the background on CalWater and on atmospheric river work, and Professor Kim Prather from UC San Diego Scripps as well will also provide some background on where this effort came from and some of the science on atmospheric rivers, and then we'll turn it over to Dr. Ryan Spackman from Science Technology Corporation and NOAA in Boulder, who will give a briefing on the details of what we're doing this coming winter from a broader perspective. And then finally, Ruby Leung, Dr. Ruby Leung from DOE PNNL, who's the chief scientist for a major project sponsored by DOE that's contributing significant facilities and resources to the experiment. So with no further ado, let me go to a couple of images here to try to get us oriented. So this highlights, just very briefly, the fact that we've got a significant amount of scientific resources going in the field coming up, and Ryan will give you more details on this. It also highlights in the background an image of the satellite image of an atmospheric river in color. And then schematically overlaid on that is this white area is a region of aerosols we're depicting schematically. The color field in the back is a real image, and you see the west coast right here. So our objectives include measuring these aerosol dust plumes and how they interact with the atmospheric river offshore, and then also when they reach the coast. I should mention that the experiment we're doing this winter has a long history, starting back in 2008, with leadership from the California Energy Commission and NOAA and Scripps. We organized what we now call CalWater 1, which was a 3-year program of studies, mostly land-based with the DOE G1 aircraft for one winter, looking really at the atmospheric rivers as they penetrate inland, and then also looking at how aerosols impact clouds and precipitation over the Sierra. And there was some very groundbreaking work. You'll hear about more of that from Kim in a moment. And then when we wrapped up that field season in 2011, so we did 2009, 2010, 2011 in the field, we realized there were a lot more science questions remaining to be answered, many of which require observations offshore. So we formed a steering committee of experienced scientists from a range of disciplines: chemistry, hydrology, meteorology, climate, and from agencies, DOE, NOAA, NASA, USGS, and universities like Scripps and Colorado State University and the Hebrew University of Jerusalem. And you can see the representatives on our science team here really represent that breadth of interest and expertise. I have to say this is really an important aspect of what we're doing. The problems we're facing in California with water, there's no silver bullet. We have to really push hard in interdisciplinary ways to figure out how the atmosphere and land surface are working. And the cutting edge of some of the science we're doing, I expect, will lead to better tools and functionality in the future. And we have other projects not related to our briefing today that are exploring that. So let me continue. Just briefly, many of you probably already are aware of the atmospheric river topic, but this is a nice schematic from Scientific American from Mike Dettinger and Laura Ingram. And really the result of about 10 years of major investment in understanding how the atmosphere is behaving. One of the interesting new results that Mike Dettinger led It has to do with how atmospheric rivers relate to drought. Turns out when we have too many atmospheric rivers, we create floods, or floods can occur. And when there are not enough, we gradually fall into a drought. And this is what Mike Dettinger showed here in this graph on the bottom, is on the left side, the gradual descent into a drought, and then a jump in the middle there where we get out of drought and into a more normal situation. It turns out that about 40 or 50% of those drought-busting months occurred with atmospheric river conditions as a key part of that. We're actually seeing that happen right in front of our eyes here in the last few weeks. We've had quite a lot of atmospheric river activity and associated rain, and the reservoirs are refilling a bit. There's still a long ways to go. An example of that was just last week. We had a significant AR event that hit Northern California, and this is a sequence over about a day, and you see the satellite imagery here with the classic signature of an AR coming in. Think of the winds blowing along that line of large water vapor content right where it intersects the coast is where the heaviest rain is. And then that sort of stalled for about 12 or 24 hours and then propagated down into Southern California. By the time it got there, it was a bit weaker, still produced a couple inches of rain. Up here, though, it produced over 10 inches of rain in 24 hours at one point. Let me highlight just a little bit on that right now. In fact, this is a case in point of the point of our press workshop here, is that this atmospheric river producing that 10 inches of rain in 24 hours roughly, and was actually in the watershed associated with a seriously low reservoir called Lake Mendocino, and this shows the 12,000 acre-feet increase in storage that occurred in 2 days. This was about enough to erase about 30% or 33% of the water storage deficit for this time of year in that reservoir. So one AR reduced the storage deficit in that reservoir by about 33% in really just a day or two. How did we do in predicting that? Here we see, I'm not going to explain the details of this, except to say that if you go from right to left here, you go farther out in forecast time. And this map, this diagram, which is a new result from our work with Department of Water Resources and NOAA and others, and Jason Cordera at Plymouth State University. The dark colors here represent about a 6-day forecast showing pretty high likelihood of an AR hitting Oregon and Washington and lasting quite a while, and then also hitting San Francisco area. So we sort of had a few days heads up that there would be an AR coming. How strong it was, exactly where it would hit, and whether it would really provide drought relief or maybe even flood risk, that remained to be determined. But I just wanted to highlight that we're starting to see indications of these things coming. And I want to highlight our new center at Scripps. If you go to cw3e.ucsd.edu or just Google CW3E, we have this product updated daily online, and you can see how things are looking for the next week or so. Now, one of the motivations for our work has to do with the issues with water management in California. We have these reservoirs which are incredibly effective at flood control and unbelievably valuable for our water supply. Since our water largely comes in the winter season in the form of these atmospheric rivers producing about a third to a half of the rain and about 40% of the snow in the Sierra, these reservoirs are kept a bit low during the winter in the case of a flood, basically a big AR that stalls and produces too much rain. And then it's allowed to refill in the spring after the flood season or flood risk season is passed. So this is what happens on this reservoir. And you see right here the amount of water that's allowed to, or the capacity of the reservoir is about 118,000 acre feet. By the way, that's about enough water for 500,000 people, or 300,000 people, or households, I should say. And in the fall, this gold curve, you see how they draw the water down if need be, like happened right here. And then this is the flood pool is maintained, and then it's supposed to refill, but this year it didn't really refill fully. Then in the summer, it's drained for water supply and fish. And then we had a big atmospheric river actually 2 years ago at an AGU conference, once again, the Thursday beforehand for whatever reason. And it refilled the reservoir substantially, but the rules say one must drain that. The Army Corps of Engineers has to drain that to recover the flood control space in case there's another big storm. Right? If you kept all that water and another one of these storms hit, you'd be over the top here and that'd be a real problem. So the rules are very well-founded in that they need to allow for water control or flood control space. But look what happened in the spring. There was no restoration of the water. There wasn't enough inflow. Turned out that was pretty much the last major event for about a year and a half. And we've been in serious deficit ever since. So the question is, can better forecasts and information on these atmospheric rivers and on the precipitation they'll produce, which includes the role of aerosols in the process, is that really possible for us to maybe do something new with the reservoirs? And at this point, I'd like to turn it over to Kim Prather. Let me adjust this if you want. I can bring your presentation up.
Thank you. Should be there. Yeah. Perfect. Thank you. Okay, well, good morning, everyone. I'd like to also thank you for coming and your interest in this topic. And I was involved in the sort of the first Cal Water and was the main scientist for understanding how aerosols are influencing clouds and precipitation. And so what I'm going to do today is give you just a bit of background on the research that sort of some of the initial findings that we have that sort of have set the stage for certain parts of Cal Water 2. So before I go too much into it, one thing we've learned is that the public, in general, the public sort of has isn't completely clear on when we say aerosols, what are we talking about? And I mean, people think about the thing that comes out of the spray can. And so I just want to briefly mention the type of aerosols that we're thinking about and the type of aerosols that are actually influencing our climate. So basically, one of the most common types globally is what's produced when a wave breaks. You can see the spray. Another type that you see that they're both naturally produced is the dust that goes around the globe. Aerosols can make it all the way around on the globe on the time scale of sort of weeks. And so they really are sort of a global issue when we think about things that are modifying our clouds, and I'll talk about that in a second. These are both examples of natural aerosols that are produced, but there's also human-produced aerosols, and those are things like soot. You can very clearly see the emissions coming out of things like cars and trucks and ships and wildfires. And so why do we care about these aerosols, and how are they influencing our climate? Well, we were brought into this in 2009 by the California Energy Commission because it was believed that the snowpack was going down, the amount of precipitation we were getting was decreasing. And at the time, people were thinking that it was the local air pollution in California that was seeding the clouds. Basically, if you don't have aerosols, if you don't have aerosol particles, you do not have clouds. And so at the center of every cloud drop, at the center of every ice crystal is a particle. But not all particles seed clouds the same. It depends on what they're made of. And so different sources are more efficient. Some sources are more efficient at seeding clouds than others. And the bottom line is at the time when we came into this project, it was believed that we were putting too many seeds into the clouds. And so when these particles go into the clouds to form a cloud, there's only so much water available. And if there's too many seeds, you make many, many tiny drops, but they can't grow big enough to fall into rain. And so it's believed that in areas where humans live, where we're producing more of these seeds, we can actually turn off our precipitation in those regions. And so I had been involved in looking at, we developed a tool that lets us look at what the sources are, and so we started flying this instrument through clouds as part of Cal Water to try and determine what were the actual sources that were leading to this change in precipitation. And as I say, we came into it thinking it was going to be local pollution, and as I'll mention in a minute, we actually found out that there were a few surprises along the way. One thing I want to mention is one of the key ingredients in precipitation is actually ice formation. And when you talk about ice being formed, it is really, really finicky as far as what it likes to form upon. In the atmosphere, only 1 in a million particles on average will actually give you an ice nucleus. And that's kind of the magic switch that enables a very efficient precipitation process. So in flying through these clouds, we were also sampling the ice crystals and the cloud drops one by one and trying to understand what was in them. So this is just a quick schematic that just shows the two scenarios. When you have too many seeds going into a cloud, you end up with many, many tiny droplets, and you can shut off precipitation versus clean conditions where you have less seeds, you can grow, you have fewer droplets, so they get much bigger, and they will precipitate more efficiently. So this was a big this was the very first study we did. It was in the Sierra foothills in basically shown here, and what we were interested in, we went out for a 2-week sort of early start, we called it, and this was the first time that meteorologists and atmospheric chemists sort of came together on a grand scale to look at this issue. And I have to say that, there was quite a bit of skepticism of whether the aerosols really would matter. I mean, if a cloud's going to rain, it's going to rain. If it's going to snow, it's going to snow. Do the seeds really matter? Those were the kinds of questions we came into this with. We lucked out in that there were two, what Marty just talked about, atmospheric rivers. They were back to back. And And one of the hard things in doing this project is figuring out why it rains or snows and understanding sort of these subtle effects. There's so many factors that play a role. It's really, really difficult to untangle the impact of just the aerosol part as we were hoping to do. But we lucked out in this case in that these two storms meteorologically were identical. By as close as you can get to identical for two storms. And the only thing that changed was the actual seeds that were in the clouds. And so basically, in Storm 1, we saw sort of evidence of local pollution. In Storm 2, we saw 40% more precipitation. And this is an atmospheric river, so that's already a lot of precipitation, and 40% more on top of that is a lot of precipitation. But one of the smoking guns, if you will, was we actually found dust in this precipitation. And we thought about it for a while because we really weren't seeing dust in our ground-based measurements. We couldn't really figure out where things came from. And in the end, we figured out that the dust came from as far away as Africa. It was actually Middle East and Africa. You can get dust that comes across the Pacific in the jet stream. And this was coming in with also biological particles such as bacteria and viruses, which are things that could be being produced either with the soil, coming out, lofted with the soil and coming across. But these also come from the ocean. We think of the ocean as just being a source of salt, but the ocean has a lot of biology, and these things also get produced and lofted into the atmosphere. So this combination came in, actually seeded these higher level clouds, formed ice, which is the critical component. That ice then is a very efficient scavenger of the moisture in that cloud. It will literally take the water off of the droplets and grow into ice crystals, which then fall. And they fall through these lower level clouds where there's lots of big droplets, and they can scavenge. They just pull all the water out of those clouds. And on days when we saw this, there was tremendous amounts of snow at the ground. On days when we didn't see this, when there were not conditions conducive to these coming in and seeding the clouds they were not nearly as efficient at precipitating. We would find tiny little super cool droplets, no ice, and those did not lead to precipitation as much. So this is what we call sort of Mother Nature's way of seeding things, and it's very different than the way humans seed clouds. We've been seeding clouds in the Sierras since the late 40s, and we do it quite differently than this. And so one of the things we hope to do in Cal Water, and I'll leave that to the other, to Ruby and Ryan to talk about, but one of the things we hope to do is really start to untangle these different source effects and how, days where we do have lots of snow, we can start to learn from, take a cue from sort of how it's done naturally, and really start to understand what does affect our precipitation processes. I will say that one interesting thing about the aerosol component, as we're seeing cases where there's more flooding in certain regions, more drought in other regions, we do think that the aerosols are potentially leading to this redistribution. There's a lot more moisture in the air. As the climate warms up, there's going to be more moisture. It has to come down somewhere. So if you've got drought in one region, you have to have a lot more water coming down somewhere else. And so we're starting to see this sort of redistribution of water, maybe coming down in regions that we aren't prepared to actually capture the water. And so these are things that we would like to try and understand more as we move towards Cal Water. And with that, I'll leave it to Ryan to talk about the facilities and the ways that we're going to approach these types of questions in Cal Water too.
So looking to the future and the next steps, we have a lot of exciting science on tap for this coming winter right in your backyard. Cal Water 2015, the field campaign, has been designed to address key science gaps, specifically extreme precipitation events along the U.S. West Coast in association with atmospheric river events like what we've had here in this region over the past 3 weeks. And another key objective is, as has been mentioned by Kim, is to better understand the role that aerosols play in modulating, how they influence precipitation not only offshore, but in particular along the west coast of the United States, in association with the precipitation in the coastal mountains and also the Sierra Nevadas. The observational strategy is depicted in a composite figure on the right-hand side. This includes all the major facilities. And I'm going to go through some of the mechanics of this before we go back to the science with Ruby's few slides toward the end. There are a number of key assets here from 3 different organizations, 3 different government agencies, specifically NOAA, DOE and NASA are involved in this effort. The NOAA research vessel, Ronald H. Brown, will be in the field for 1 month, coming out of Hawaii and cruising toward the east, toward just a few hundred miles off the west coast, around 128 degrees west latitude. And it will include, it will host the Department of Energy's ARM mobile facility, which is an integrated observing system for aerosols, trace gases. It will include LiDAR measurements and radar measurements, giving you precipitation information, information about where clouds are located, providing context in the vicinity of atmospheric rivers as they pass through. Of course, the ship will not be making a lot of motions here. The idea is it stays stationary and the weather passes through it. In addition to that, NOAA will be contributing the P-3 aircraft, called the Hurricane Hunter, as you may know from tropical cyclone research, and also the NOAA Gulfstream 4 airplane. Both of these aircraft will be providing meteorological support for the Cal Water Science efforts to address atmospheric rivers and also to better understand aerosol impacts on precipitation. So some of the instruments involved, dropsondes are a key component of this. Dropsondes are released from the airplane, descend on a parachute. They give you information about temperature, relative humidity, and also wind direction and wind speed, all very critical to understanding the thermodynamics in the atmosphere and specifically understand the processes controlling the structure and evolution of atmospheric rivers. Other additional measurements include precipitation and cloud radar information, and we'll also have some limited chemistry in the form of ozone. The DOE G-1 aircraft will be operating from Sacramento at McClellan Airfield together with the NOAA P-3 and the G-4. The G-1 will be providing aerosol and microphysical information, which will be operating in the coastal regime near offshore and also over the Sierra Nevadas, probing the interaction of the moisture as it makes landfall along the west coast and the aerosols that are oftentimes above that moisture level but then are forced to interact as the moisture is forced up the mountain slopes, resulting in sometimes enhanced precipitation. The other element here to draw your attention to is the NASA ER-2 aircraft will be involved thanks to efforts at NASA Jet Propulsion Laboratory and will include cloud and aerosol remote sensors to provide the greater context for these observations. So the Cal Water 2015 field campaign has a very unique development story, in my opinion. It didn't happen overnight. It was a systematic, I would say incremental sort of development that was largely based on the establishment of the NOAA Hydrometeorological Testbed Network, which is a integrated observing system including meteorological information with information about precipitation and also wind profilers to provide the greater context for the meteorology when an atmospheric river makes landfall. All these individual dots here represent some of those measurements along the West Coast, in particular in the state of California, in large part supported by the California Department of Water Resources. Another important point here is the National Science Foundation has supported an effort to deploy aerosol chemistry at a site just north of here at Bodega Bay on the coast, which will add a tremendous amount of value to understanding the role of aerosols in these precipitation processes right along the coast. The Department of Energy committed the G-1 aircraft, which is pictured right here next to Ruby, which will carry an aerosol microphysics payload, and that'll be probing, as I mentioned before, right along the Sierra Nevadas and coastal mountains. They also committed what's called the ARM mobile facility, which is an integrated observing system of, as I mentioned, aerosols and trace gases, LiDARs, radars, that will be hosted on the NOAA Ron Brown. NOAA also contributed the NOAA P-3 and the NOAA G-4 to provide offshore and to some extent onshore support for the meteorology when an atmospheric river makes landfall. And then more recently, the NASA ER-2 joined the scene with cloud and aerosol remote sensors. And this is the nominal timeline we're talking about for these activities, all in early 2015, from mid-January through mid to late February into early March for some of the aerosol studies when a lot of the long-range transport of aerosols becomes more prevalent toward the end of that period into March. And my last slide here shows you the facilities summarized in the left-hand column. These are the airborne and ship activities. As I mentioned before, there's a ground-based network of meteorology along the coast here in California and also in the Pacific Northwest, and also the Bodega Bay site with aerosol chemistry just north of the Bay Area. This is an integrated water vapor loop. Note this is from last year when one of the major atmospheric rivers, one of the only major atmospheric river event, made landfall here along the West Coast, showing you a classic atmospheric river, not too different from what we saw here last week. The Ron Brown will be leaving from Hawaii on January 14th, and in a week's time we'll be on station just off the West Coast here, and at the same time that the Ron Brown leaves Hawaii, we'll have the NOAA P3, the NOAA G4, and the DOE G1 descend on Sacramento and operate out of McClellan Airfield. And we'll also have the NASA ER2 operating out of NASA Armstrong Flight Research Center in Palmdale, California. And then the Ron Brown will be out for about 1 month's time and arrive in San Diego on the 12th of February for unload. The aircraft activities will continue into late February and the G1 into early March. So I'd encourage you to stay tuned for more activity this winter. And with that, I'll turn it over to Ruby.
Okay, so exciting, right? So many different aircrafts. We have 4 different aircrafts. We have a research vessel. We have over 100 different instruments going on during the January and February timeframe of the field campaign. So what are we going to do with the data? So that's what I'm going to tell you a little bit about. So remember that when we have an atmospheric river condition, as Marty and others have already talked about, so we have winds, so wind speed is really important. We have moisture amount being transported in really narrow filaments out from the tropical area to land. And then we also depend on the atmospheric stability, meaning that whether your air parcel is unstable or not, whether the air can actually rise and produce precipitation. So these are 3 important ingredients for producing heavy precipitation. So the problem right now is, we use models to forecast what is going on and what will happen, and we also use models to tell us what might happen in the future when the climate may not be exactly the same as what we have now. Are these models good enough? Can we really use the models to tell us what might happen in the future? So during the cold water field campaign, so again, we will be observing these atmospheric river conditions. So the 3 major platforms that we will use to look at these ingredients here in terms of wind, moisture amount, and also atmospheric stability. So this would use the research vessel, Ron Brown, out in the Pacific Ocean, because this is where the atmospheric rivers come from. And we would also have this instrument, the DOE Arm Mobile Facility, where we will be probing from down below, looking at what is going on up there. And we would also have the NOAA aircraft. So these would be providing us with a lot of data. And what are we going to do with that? So we would be analyzing the data, of course, and we would also be running big computer models. So these big computers models, they have all kinds of processes going on inside, representing what are in the clouds, the radiation, the air mass, the evaporation coming from the surface, from the ocean surface, etc. So using these big computer models running over big computers would help us to understand the data that we are collecting, as well as using the data to tell us whether the models are doing a good job or not. So this would be one element, is how much precipitation would be produced. But the second important element that Kim talked about a lot is aerosols. So that really helps us answer another important question, is will the precipitation come in as rain or snow? And of course, whether the precipitation will come in as rain or snow depends a lot on the temperature. But also what we found is that these transported aerosols that might come from really far away, for example, dust, is really a major determinant of whether the precipitation is going to come down as rain or snow. And why is it important? Well, as you know, in the mountainous area, a lot of the precipitation does come down as snow. And the snowpack captured in the mountain is really important for for refueling the reservoirs, and then these would provide us with the water supply in the summertime. So understanding whether we are getting snow or rain is a key question that we are going to answer. And so for this, we would be using these 3 aircraft, the NOAA, the 2 aircraft P3, as well as the NASA ER2, and then the DOE G1 aircraft, which, as we said, we have a little model over here that you can look at later. So when you look at this picture here, you might think, okay, yeah, we are seeing an atmospheric river. Are we seeing an atmospheric river? Actually, this is a computer model simulation of dust transported from far away. And it does look like an atmospheric river, right? And that's because both long-range transport of dust and also atmospheric river are affected by a phenomena called the jet stream. So essentially, the dust hitch a ride from the jet stream and come all the way, and which is why you are seeing things kind of similar to a feature of an atmospheric river. So we would like to know, like, how much dust actually come from where, and how are they affecting the precipitation amount as well as the phase of the precipitation, whether it is rain or snow, and what might happen in the future. And so just summarizing here, so these are the key questions that we are going to answer again. So related to atmospheric rivers, how much water vapor is transported by the atmospheric rivers? And where are their sources? Are they really coming from the tropics? How much of that comes from the ocean by evaporation? What processes control precipitation when the atmospheric river makes landfall? And then the second kind of question related to aerosols, how they affect cloud and precipitation. What are the distribution, the characteristics, and also the sources of aerosols that affect wintertime precipitation in California? How do aerosols influence precipitation in different regimes during atmospheric river condition versus not an atmospheric river condition? And then lastly, how are they collected? I mean, do the dust or other type of aerosols out there in the ocean actually affect the evolution of the atmospheric rivers? I don't think we have addressed this question ever before. And then the last one, how well can models really capture all of the above so that we have better faith in doing our weather forecast as well as the long-term projection of what might happen in the future?
Okay, we're ready for questions from the press.
Mary Miller from the Exploratorium. You mentioned that Ron Brown will be on station. What happens if the atmospheric river doesn't go right over Ron Brown?
The Ron Brown can move about 2 to 5 degrees of latitude in a day. So we're going to be predicting the storms a few days out as best we can, and then fine-tuning the position of the ship and the aircraft flights up to the day ahead and even hours beforehand.
Rick Levitt, freelance. I'm interested in the aerosols in the snow. What is the mechanism that, I mean, I come from Oregon. I thought that the snow line was dependent on temperature. And so what is the mechanism that can cause aerosols to affect what you're essentially talking about is the snow line, I think? Or does it kick the snow to higher, the precipitation to higher elevations?
Sort of all of the above. What happens, and the first thing you look at, you have to look at the temperature, right? Because if if it's really warm near the ground, even when you start as ice, it can melt, right? So it's not always snow, but we do see that that under sort of similar conditions where you have the same ground temperature, but in one case you have dust, in one case you don't, we will see more snowfall when the dust is there. The mechanism by which it happens, part of it is just that you're starting out as ice, right? That's what the dust and the biological material like bacteria give you. So if you start as ice, that ice is just growing and riming as it falls, and it ends up being these big ice sort of chunks and crystals that can make it all the way to the ground. And it does affect, if it falls as snow, it's affecting where your snow line is for sure. And this is happening. You say you're from Oregon. I mean, this will, we've been looking at it in California, but it will happen up and down the coast. Some people ask us what happens if there's not a storm in California. Will it make it further to like Colorado? We're now, the implications of the area over which this can happen is actually quite large. But it's just, the key is that ice, forming that ice is what seems to lead to a switch to the snow, making it all the way down.
Hi, Kit Stoltz, Santa Barbara Independent. Two questions. One, sort of where are we in the state of knowledge? Are these early days in AR forecasting, or are we fairly far along? And second question would be, how much is this particular effort costing?
Yeah, the last question first is that for the deployment costs, we're on the order of about $5 million. If you factor in the time to do some analysis and planning, it's on the order of 10. So 5 to 10 million. And it's really contributed from different agencies supporting their internal people, supporting some contracts and grants. It's very much a community effort. And thanks to everybody for the contributions. Regarding the AR science and prediction, we're about 15 years into learning about it scientifically. We've started developing some forecasting tools tailored to ARs. I showed you one a moment ago. And we're working heavily with Department of Water Resources here in California to further develop those methods. I would say that the first evaluations are that the forecast models are pretty good at representing whether there's going to be an AR in the Eastern Pacific or not a few days ahead. We have a study just published by Wick et al. That shows a 5 days lead time. There's about 500 kilometers uncertainty in the landfall position. So that's like saying 5 days ahead, we think that an AR is going to hit California, but we're not sure if it's going to be Santa Barbara, San Francisco, or Eureka. And as the storm gets closer, we're able to narrow it down to more like 200 kilometers. And our target is to really improve on all of that. Now, getting the AR position is really vital, but it's not the whole story. Because you can have a good atmospheric river transporting lots of water vapor right into the mountains where it's primed to create precipitation. But these aerosol-related processes need to also be active, and we think those are modulating how much precipitation ultimately comes out of the AR when it reaches shore. So one of the roles of the experiment here is to really measure the ARs accurately offshore better than ever before, measure the aerosol influence, compare these to models, and compare them to these new observations in the state of California supported by DWR. I don't know if that gets...
More questions? Any questions from the chat? Oh, questions from press. Are you with the press?
Well, I'll ask another question, Rick Lovett. What do the models show as changes in the dust? I gather dust counts as an aerosol. What do the climate change models show as potential changes in this that we should be looking for that might really affect these models?
Well, I guess I could answer that a bit. So right now, we use, as I mentioned, we use big computer models to do this type of prediction into the future. And the emission of dust depend on a few factors, including like the winds. If you have stronger winds, you would have more dust, and also depend on this, on how moist the soil is. If you have like moister soil, then it wouldn't emit a lot. So all of these changes, including like how strong will the wind blows in the future, how much soil moisture would there be in different locations and things like that. So those would affect the prediction of dust into the future. And I would have to say that right now we still have quite a bit of uncertainty in the climate models, especially in terms of predicting these kind of factors, because they are quite regional in a sense. It depends on the surface winds rather than the large-scale big wind systems system. It depends on the soil moisture, which depends a lot on precipitation, which are quite local. So part of it is to increase the resolution of a model so that they can resolve these kind of processes that are much more local scale. And also gaining the knowledge about what processes control this type of emission and the transport. Those are all important, and these are the kind of data that we hope to get in order to improve our models.
I'll add a little bit to that. Also, not all dust is equal. You have different mineralogy depending on which deserts they're coming from, and so certain dust is better at forming ice than other. And in particular, aluminosilicates, which come from Africa, are very effective ice nuclei. And so understanding, the emission patterns, as Ruby mentioned, is important. But climate models right now don't take the mineralogy into account yet. So it's getting the wind fields right, getting sort of how things are lofted. There's a lot of people working on that side, but then once you get things lofted, figuring out how effective they are at actually making ice is going to be sort of the next step, and that's something we're just starting to touch on now.
Rex Sanders, freelance. Two kind of questions. Tagging on to that one, cloud seeding, there's a lot of controversy about whether it works or not.
Sorry.
But if you were able to predict that an AR was coming along that didn't have sufficient particulates in it, would there be a potential application for doing cloud seeding and on this kind of scale? Has anything even been attempted like that?
I think that's a question that gets asked quite a bit, and I think, as you say, we do cloud seeding now, and we've been doing cloud seeding for a long time. Humans do cloud seeding quite differently than what we've seen here, and so one of the things we're trying to learn about, I say before I would be comfortable completely saying that this is doable, the thing that we have to do, the steps that have to happen, is that we have to understand we need more observations basically of these kinds of events, because this is weather and you need multiple data points. But if we can take sort of lessons learned, see these types of storms, more of them, then we can start to really basically get sort of a mechanistic understanding of what's going on. We can do that. The key is that we have to improve the models. We have to get the weather forecast models, the engine inside the weather forecast models, to be able to handle the observations we have so we can improve them. Because there's so many moving parts in what actually leads to water or snow coming out of a cloud, right? We can't just say, dust in automatically will give you this out. There's so many parts to that, right? And so the models have to get better. And so that's what we're trying to do, is to have enough observations to where we can improve the models, the weather forecast models in particular. When does it matter? When the dust is there? At what point in the storm? At what altitude? And those are all things that you can tweak in a model if you can get those kinds of processes right. So that's what we're going to try and do in CalWater too.
Kim, if I could add just one point to that. If you look at the satellite images showing dust coming across the Pacific, you see that they're in fairly wide swaths. If you think about the human scale, these are hundreds of miles wide. To get man-induced seeds spread out over an area like that is not something that's traditionally been very feasible. I doubt, maybe it's going to be very tough to do, but I think Mother Nature has done a remarkable job in seeding these clouds in large areas right when we need it, right when it's most efficient. And I'm saying that partly because there was a study called the Sierra Cooperative Pilot Project some decades ago that looked for several years with lots of resources at whether cloud seeding worked or not in the Sierra. And the lead scientist for that concluded that Mother Nature was remarkably efficient. When there was an opportunity to seed clouds, Mother Nature seemed to take care of it. So there wasn't a lot of margin left for people to make a difference. Now that's still a hypothesis. There's a lot of work to be done. But I would say we're learning a lot more about when those opportunities might be there that could make things more efficient if it's done right.
And then the second question, have you scheduled an AR for this time period?
AGU does that for us. We put it right. It's funny, actually. In 2010, we had our first ever special science session on atmospheric rivers at AGU. It was on a Friday in the afternoon, the worst slot, basically. And guess what? Friday evening, a massive AR hit, ended up dumping 20 inches of rain across Southern California, caused flooding in Utah, and ended up being a case that we've now published and learned a lot from. Fast forward 2 years, and we had our first ever atmospheric river press conference, and it was related to the Department of Water Resources and NOAA and Scripps network that's going in place. We were announcing it's largely installed, and 3 days before that press conference, we had the last big atmospheric river to hit California. Now, 2 years later, we had a even bigger session and another press conference, so sorry to make a joke about this, but it does seem sort of funny. Every 2 years in early December around AGU, we've had, a couple good events.
The question I was really trying to get at, though, is how certain are you, or have you calculated the probability of an AR during this monitoring period when you're going to have the assets available?
Yeah, we have done quite a lot of work on that to help identify how feasible our experimental design was. And we anticipate within the reach of the aircraft and ship, we should be able to have on the order of 4 or 5 AR events over the 6 weeks or so we'll be in the field. And that's possible partly because we can move around and go get them. Now, how many will hit California during that time and reach our areas on shore? Probably 2 or 3 would be a good estimate based on climatology. Normally, there are about 6 to 10 ARs hit Northern California in the winter, and we're going to be operating for about a third of that. I did have a couple other data points that never came up yet, and I forgot to mention one of them. One is that the drought issues in California have been so severe. I've been tracking a little bit the reservoirs, and there's some real experts here. Maury Roos, the former chief hydrologist for the state of California, and Mike Anderson, the state climatologist also. If I've got this wrong, guys, correct me. But just watching some of the data come in over the last week since the last AR, there's been about 500,000 acre-feet of additional water put into the reservoirs, 6 of the big reservoirs in Northern California. Over the last 30 days, it's been over 1 million acre-feet. And this isn't counting every reservoir. These are just the major ones. That looks to me to be on the order of about a 20 to 25% reduction in the water storage deficit in those reservoirs at this stage of the game. So, the recent events have really made a dent, in my humble opinion, but there's a long ways to go still. So ironically, we have drought going on, in my mind, from a reservoir storage perspective, while the ground is getting soggy, up north.
Are there any more questions? Anyone? We're about to wrap up. If there's something that someone desperately wants to ask, here's your chance. Okay, well, thank you, speakers, and thank you to everyone else for participating.
Thanks, everybody.
Thank you.